Jared is a farm manager. He produces corn and he has a target of 60 bushels. His production function is the following, where L is labor in man hours per month with a wage of $4,000 per month, and K is the machinery in also hours per month at a rental rate of $2,000 per month. Here we need to find first the marginal productivity with respect to labor and then with respect to capital. And then we will use this relationship to find the solution to the problem. This relationship comes from the cost minimization property, in which the marginal rate of technical substitution is the ratio between the marginal productivity of labor and the marginal productivity of capital, and that must be equal to the ratio of the input prices, which are wage and the rental rate. And then we will solve the problem using constraint optimization. In both cases, we need to know what is the optimal allocation for labor and capital and what is the optimal cost. Here we have a cost minimization problem in which the cost is equals to the money spent on labor and capital. Remember that the wage was 4,000 and the rental rate was 2,000, subject to a production function that has a target of 60 bushels. First, we will solve this problem by using the relationship of the marginal rate of technical substitution, which is equals to the ratio between the marginal productivities, and that must be equals to the ratio of the prices. To obtain the marginal productivity with respect to labor is simply the derivative of the quantity or the production function with respect to labor. Here the constant part is K 1/3. Then the derivative with respect to labor is 2/3 L to the minus 1/3. Then the marginal productivity with respect to capital. This is the derivative of the production function with respect to capital. Here the constant part is L to the 2/3, and the derivative of K to the 1/3 is 1/3 K to the minus 2/3. The marginal rate of technical substitution is the ratio of the two. So here you can see that we can divide or multiply actually everything by 3, and these two cancel out. Then this is 2 divided by 1 is 2. Then L, 2/3 goes to the numerator as a negative 2/3, which is minus 1/3. Minus 2/3 is minus 1. And then we have K, 1/3 plus 2/3 is equals to 1. In other words, this is 2K over L. This marginal rate of technical substitution has to be equal to the ratio between the wage and the rental rate. The wage was 4,000 and the rental rate was 2,000. So here you can see that this is 2, which cancels with this one. This means that K is equal to L. And we'll replace that relationship in the production function. So we had here Q was equals to L 2/3 k 1/3. But remember that we already have a target. The target was 60. And here we have that k and l are equal. So we can write instead of k, l. Notice that l to the 2/3 times l to the 1/3 is simply l. That means that l is equals to 60, which is equals to k. So this is step 1, this is step 2, and finally in the third step, we just find the optimal cost. This is 4,000 times 60 plus 2,000 times 60. So this is equals to 360,000. So that is the optimal cost. Now let's solve our problem using constraint optimization. Remember that in order to use it, we need to have, in the case of the restriction, everything equals to 0. So what we can do is, for the case of this restriction, we move everything to the right hand side. And in that way, our restriction is equals to 0. So let's start by plugging the Lagrange function. Here we need to insert our objective, which is 4000L plus 2000K minus lambda times the restriction, which is 60 minus L to the 2/3 K to the 1/3. And we have three variables, L, K, and lambda. So this was the first part. Now let's obtain the first order conditions. With respect to L, here the derivative is only 4000 minus lambda times. Here the constant part is minus k to the 1/3, and the variable part is the derivative 2/3 L to the minus 1/3, and this must be equals to 0. Let's continue with the Lagrange with respect to capital. So this is going to be only 2000 minus lambda times. Here minus L to the 2/3 is a constant part, and then the derivative of k to the 1/3 is 1/3 k to the minus 2/3, and that must be equals to 0. And finally we have the Lagrange with respect to lambda, which is minus 1 times 60 minus L to the 2/3 k to the 1/3, which must be equals to 0. And let's rearrange these relationships. So here we have that 4000 will be equals to negative times negative is positive, but because we are going to move it to the right hand side, this is 2/3 negative L to the minus 1/3 k to the 1/3. Here we have 2000 equals minus 1/3 L to the 2/3 K to the minus 2/3. And finally here we have 60 equals L to the 2/3 K to the 1/3. And you know that because you will always get the original restriction. Let's divide these two in the next page. So let's divide these first two equations. Here we can cancel the negative sign and the 3's. And notice this. 4,000 divided by 2,000 is 2 equals, here we have only 2, L minus 1/3 minus 2/3 is minus 1, and K 1/3 plus 2/3 is 1. So here we have 2 divided by 2 is 1. So 1 is equals to K over L. This means that K is equals to L. And we use that relationship here. So here we had 60 is equals to L to the 2/3, and instead of K we can write L. And because it's the same base, we can sum the exponents, and 2/3 plus 1/3 is 1. So this means that L is equals to 60, which means that K is equals to 60. And finally, we can obtain our optimal cost by simply replacing the values of L and K in the cost function. So here we have 4,000 times 60 plus 2,000 times 60. So this is equals to $360,000. And as you can see here, we obtained the same answer as using the Lagrange optimization and the marginal rate of technical substitution relationship with the ratio of the prices of the inputs. So both methods should provide the same answer.